This is the vision of the apocalypse, according to a theory known as the Big Crunch.
What's happening with the Big Crunch scenario is that all of the matter in the universe and all of the energy, the galaxies, the stars in them, are all moving back towards each other, and the universe is shrinking. Things are getting closer and closer together.
Our universe right now, on the other hand, is expanding. Each day, there is more and more space as galaxies get further and further apart. The opposite happens during a Big Crunch.
The space between things is shrinking, and that's rather like filling up this hallway with people. And there are more and more people, the space between them then is getting smaller and smaller. They bump into each other, they're trying to dodge out of each other's way, and so everything is heating up and getting more and more energetic as more and more things happen in this small space. Exactly the same thing would happen in the Big Crunch scenario, where various particles that make everything up are bumping into each other more frequently. The galaxies and the stars, they're getting closer to each other to start distorting each other, and so the whole thing's beginning to heat up, just like a crowded room would heat up. The process continues with the temperature of the universe getting higher and higher to the point that the atoms themselves begin to fall apart.
Finally, our vast universe collapses into a microscopic point.
We'll end up with this soup of matter which is made of fundamental particles which are milling around at high energy, high temperature.
Life as we know it has no escape. However, the universe may not ultimately ignite into an all-consuming hellfire.
There are two basic paradigms for the end of the world. First, the universe is going to end in fire. That's the Christian theory of Armageddon, fire and brimstone and the second coming. But the Norse also had their legends. They had the legend of Ragnarok, twilight of the gods, where there would be this monstrous snowstorm that would engulf the entire universe. There would be this great battle in heaven, and even Odin and even Thor, and all the great gods would slowly die one by one, and we would all die in a great freeze when even the gods themselves are frozen.
Whereas the Big Crunch fits the Christian vision of the end of days, science also has a different theory, that it may instead all end in ice. Ultimately, it depends on whether the momentum of the expansion of the universe can overcome the collapsing attraction of gravity. Imagine that the moment of contact between bat and ball is the initial explosion of the Big Bang.
Everything's being thrown outward, and the issue is, will it recollapse upon itself, or will it continue to expand? And those two possibilities are very similar to what happens when you launch a ball into the air. I launch it upwards, and if gravity is strong enough compared to how much energy I put into that initial launch, it'll pull it back down. And that's like the universe expanding out for a while and then crunching back in.
But the Big Crunch doesn't have to be the end of everything.
If the universe collapses, what might subsequently follow is another Big Bang, another expansion event. And that might expand for a while and then recollapse.
So you can imagine the possibility that actually the universe is just cyclic. And so it expands and then contracts.
Each bounce is another Big Bang. But what if there isn't enough gravity to rein in the universe?
I launch it upwards with enough energy that it completely escapes. There's not enough mass in the universe to make it recollapse, and so it continues to expand.
Eventually, though this expansion ought to slow, shockingly, scientific observations reveal something completely different. It's getting faster.
The universe seems to be careening out of control. This expansion is accelerating, it's kicking in once again. We are undergoing an inflationary expansion.
So the universe, we now know, is expanding with this extra acceleration that is beyond what you would have thought was just due to the initial explosion. Not only does the ball escape, but it's as though a little rocket engine was on the ball, and it accelerates away from the Earth even faster. This is a possibility that was somewhat unexpected.
The volume of space in the universe seems destined to increase forever.
What this means is that distant galaxies are going to go zooming away from us and will eventually become invisible because they'll be too far away to see.
And without seeing galaxies rushing away from each other, future civilizations will lose all sense of history. They won't know that there was ever a Big Bang.
So you will think that the only structure within the universe is the Milky Way galaxy, and that the rest of the universe is effectively empty, devoid of stars.
Another scientific theory proposes that this expansion will balloon even faster. If this does happen, a violent end awaits our cosmos.
Suppose the amount of repulsive energy increases with time per unit volume. It'll eventually grow strong enough to cause clusters of galaxies to get ripped apart. And then galaxies themselves will get ripped apart. The stars will start flying away from one another, no longer held together by gravity. And then planetary systems like our solar system will get ripped apart. And then stars and planets will get ripped apart. And then humans will get ripped apart. And then the very atoms of which we are made will get ripped apart. That's called the Big Rip. And it's a really scary possibility. But don't worry, most of us don't think it's going to happen.
But even if the rate of expansion never reaches this tipping point, the future of our universe still isn't promising.
Its temperature decreases. It's getting colder and colder, and darker because the feeble light emitted by stars is going into a progressively larger volume. So the universe is going to get really cold and really dark. Basically a pretty gloomy place.
The universe itself, we now believe, will die in ice rather than fire. We think the universe will die in a great freeze, just like the Norse legends foretell, rather than this Armageddon of a big crunch.
If the universe continues on its present course, we're destined for a cosmic ice age where sunlight itself goes extinct. By the year 100 trillion AD, the last remnants of human civilization may be forced to settle here, in this distant dark corner of our galaxy. They'll be huddled around the last burning star in the sky, but sadly, it too will soon die. Our Milky Way, so named for its shimmering band of sparkling stars, will be unrecognizable. Faint glowing embers of dark stellar husks will be all that remain of what was once a brilliant night vision. What happened to all of the stars? How did we arrive at such a dismal scenario? Science decrees that as our universe expands and ages, it will cool. Inevitably, the future for life as we know it will grow ever more hostile.
We are headed for a time when one day the universe itself will freeze to death, and all life with it. And that's a law. When we scientists look at the evolution of the universe, some critics say, that's crazy. We can barely predict tomorrow's headlines, and here you are predicting what's going to be happening billions and billions of years from now. How do you do it?
Among the tools available to scientists pondering the future are the venerable laws of thermodynamics.
The first law says that total matter and energy are conserved. In other words, you can't get something for nothing. There's no free lunch.
So it turns out that the total amount of matter and energy in a system can be neither created nor destroyed. The matter and energy can change forms, and they can turn into one another, but the total remains the same. So for example, in this rolled up newspaper, there's a lot of energy stored in the chemical bonds of the paper. But if I ignite the paper, I can activate those bonds and I can start breaking them, and that releases energy in the form of light and heat, which you can see and feel. The total energy content is still the same, but it's being dissipated out into space. And a lot of particulate matter goes off as well, and smoke goes off. But if I were to add up all the smoke and the particulate matter and all the energy that's given off and everything total, I would get exactly the same amount of mass and energy total as I had to begin with. They simply changed forms.
If the total amount of mass and energy remain constant, this seems to imply the universe will always have energy and should last forever. But the second law of thermodynamics crushes this notion.
The second law of thermodynamics is the most curious of all. It says that total amount of disorder or entropy always increases in the universe. In other words, things rust. Things decay. Everything gets old and eventually falls apart and rots. In some sense, the second law is a death warrant. A death warrant for the universe. Second law says all things must pass.
The ever-present supply of energy in the universe inevitably becomes more dispersed, more chaotic, and more unusable. Each star burning in the sky, just like each briquette of this charcoal, must one day face its fate.
This piece of charcoal is fuel. It has a lot of energy concentrated into this small little packet here. The energy goes from being in the chemical bonds of the charcoal briquette to being liberated in the form of heat and light. Now, a star does a similar thing. It doesn't burn in a chemical sense. Instead, in a star, it's nuclear energy. The nuclei of atoms are being forced together, fusing them, creating new nuclei, and in the process, transforming some of that matter, some of that mass, into the radiated energy that we see and we feel. And the same process is going on in all the active stars in the universe. Now, as this charcoal is burning, the fuel is getting used up, and you can actually see that. It's turning into a gray color, it's turning into ashes. In a similar way, stars use up their fuel. They fuse hydrogen into helium, and so with time, there's less and less hydrogen to fuse, and the ashes have less energy content and thus are either harder to burn or release less energy during the burning process.
This is the eventual fate of our own sun. As it ages, it bloats and heats.
The Earth will be fried to a crisp. Oceans will boil away, all plants and animals will die, rocks will start vaporizing because the sun will be producing so much light, so much energy. That'll be a pretty gruesome death for the Earth.
All through the universe, stars that are like the sun are going to be facing the same challenges that our own star will face. They're running out of fuel, they're swelling up, and they're causing problems for the planets that orbit them. So it's not hard to imagine that there are many locations where life has evolved and flourished and is now being extinguished.
Just as each star suffers the effects of entropy, so too will the rest of the universe.
But stars naturally increase the entropy of the universe by giving off light and heat, just like this fire of burning charcoal naturally increases the entropy of the universe.
Right now, we're kind of in a steady period in the universe where stars are born, live out their lives, die. give some of that gas back to the next generation, then you have another generation of stars.
But that rate of star formation is gradually decreasing with time. And as stars use up their fuel and burn out, there aren't enough new stars being formed to replace them.
But the moment we run out of gas to make new stars, it means for every dead star in the rolls, in the ranks, there's not a star to replace it. And so that's a bad situation to be in the day that happens.
So effectively, galaxies, giant collections of stars, are growing progressively dimmer with time on average. And eventually, when the universe is something like 100 trillion years old, there will be essentially no stars still shining. The universe will be cold and dark indeed.
Any life that depends on sunlight will rapidly go extinct as the universe continues to age and as there are fewer sources of life providing energy from a host star.
You might think the most massive stars, the ones with the most fuel, will last the longest. In reality, the more fuel a star carries, the faster it burns through it. The final rays of sunlight left in the universe will come from stars known as red dwarfs. These miniature stars, 10 times less massive than our own sun, burn thousands of degrees cooler.
Red dwarf stars are much more miserly with their fuel consumption, and so even though they have less fuel to begin with, they last much, much longer than our sun will last.
A typical red dwarf can live for as long as 14 trillion years. That's 1,000 times longer than the current age of our universe. Eventually, though, even these stingy little suns will begin to die off.
So when our Milky Way galaxy is tens of trillions of years old, and there's only a few red dwarfs remaining, you might imagine that any surviving civilizations will realize that the end is nigh, and they will start crowding around these few sources of energy, trying to scrape out an existence.
Red dwarfs could be oases of life in the vast, inhospitable desert of the universe. But for a planet to receive as much heat and energy from its red dwarf host as our Earth does from the sun, it would need to orbit so closely that one full year would last just 6 Earth days.
The sky would be much more sort of whitish red than our blue skies here on Earth, because the red dwarf puts out so little blue light, you wouldn't be able to have the kind of nice blue skies that we have here now.
However, nothing left in the universe would be hotter or brighter.
So there will be a time in our galaxy when there's just a few red dwarfs still glowing, and maybe just then 3 and 2 and 1 as they blink out. And gosh, when there's one red dwarf left, and suppose I'm on the planet circling it, I'll think, man, oh man, what a lonely place the universe is, what a depressing future it holds.
What happens after the last red dwarf blinks out of existence? Life in the 21st century on Earth thrives within a universe that has existed for about 14 billion years since the spark of the Big Bang. But that's no time at all in the grand scheme of the cosmos.
If the universe is comparable to a human lifespan, we are still in the infancy of the universe.
Getting a grasp of the time that has already elapsed and the time span still to come can boggle the mind.
To gain a perspective of the vast timescales of the universe, let's compress the roughly 14 billion year history of the universe into one normal calendar year. But we'll call this a cosmic calendar. So the Big Bang occurred on New Year's, January 1st. On that scale, our Milky Way galaxy formed near the end of January, and our solar system formed around the beginning of August or so, about 2/3 of the way through the year. Life formed sometime a little bit later in August, But humans formed less than a day ago. So on December 31st sometime, humans finally arose.
We can also look into the future on the same cosmic calendar timescale.
Near the end of January of this coming year, our Earth will become quite inhospitable. By around May or so, our sun will have died. But there are some other stars, the low-mass stars, which will live for much, much longer, up to 10,000 of these cosmic years.
That's 10,000 times longer than the entire history of the universe before these final longest living red dwarf stars die off. But then what happens?
When we talk about the extremely distant future, we're talking about immense spans of time, time measured in quadrillions of years and septillions of years. And it becomes so overwhelming that we need to evolve another concept to really deal with it. So we came up with the idea of cosmological decades. A cosmological decade, each decade is 10 times longer than all the time that happened prior to the start of the decade. And one way to think about this is it's like a staircase. Not an ordinary staircase like this one, but one in which each step is 10 times higher than the step before. So you can imagine this staircase going up and up and up to higher and higher cosmological decades. Right now, we're living in the 10th cosmological decade.
On this scale, the 10th cosmological decade is 10 times longer than the previous 9 decades combined that have passed since the Big Bang.
The hallmark of the 10th cosmological decade is the fact that stars are burning brightly in the night sky, and also that the planets are beginning to develop life and intelligence on their surfaces. Another interesting hallmark of the 10th cosmological decade is the beginning of the acceleration of the expansion of the universe.
As our cosmological decade continues, all of the other galaxies disappear from view, and stars begin to die off without being replaced.
During the latter part of this era, there will always be about 50 stars shining in the galaxy at any one time. And that'll be the last sort of gasp of the kind of world, the kind of planets, the kind of environments that are familiar to us.
As we move through the succeeding cosmological decades, and after the last star dies, we enter a new alien age.
So up here, we're in the cosmological decade 20 through 30. And if we look out at the night sky, it's absolutely, utterly, completely black. But if we're able to look in light that's far too red for the human eye to see, then we would actually see that the sky is speckled with dead stars. This is the degenerate era.
In the degenerate era, the most massive dead stars have collapsed into black holes. But punctuating the total blackness of space, the leftover ashes of once bright stars are still ebbing energy.
These ashes are called a white dwarf. Now they're really weird because you've got something like half the mass of our sun, roughly 160,000 times the mass of our Earth, compressed into a volume just the size of the Earth. So it's very dense stuff. It's weird ashes, that's for sure. So it'll be like the dying ember after a fire. It'll be generating no new energy of its own through nuclear fusion.
But as the dying embers of a white dwarf cool, they still emit many megawatts of power.
But that is vastly, billions, trillions of times less energy than the sun is producing right now. And so if we think we have an energy crisis now, the energy crisis in the degenerate era will be far more severe and far more profound.
Even so, the energy emanating from these ancient star remnants is still greater than that consumed today by all human civilization.
If If we were to imagine that somehow a human civilization were to persist into the degenerate era, they might be tapping the energy that's emerging from the white dwarf.
However, humans wouldn't be able to establish an energy-gathering outpost on its surface, such as an oil rig anchored to the ocean floor.
The surface gravity is incredibly strong. You would basically be crushed if you tried to stand on the surface of a white dwarf.
To survive, future civilizations would need to establish an orbiting colony.
They would probably tap that energy that's coming from the white dwarf by having some sort of absorbing panels that are also in orbit around the white dwarf. So the energy that's emanating up from below would be captured and trapped and used.
Still, light in this white dwarf orbiting future would have to be generated artificially.
There's no stars shining in the sky. There's no moonlight. There's no sunlight. You're simply orbiting a gigantic, dead, black mass.
Unfortunately, dead black masses will make up the bulk of galaxies during the degenerate era.
So as we go into the degenerate era, we'll have roughly 100 billion dead stars orbiting each other in a giant elliptical configuration.
Occasionally they'll interact with one another and one will get flung out of the galaxy, causing the galaxy to lose mass. The galaxy, in a sense, will evaporate slowly with time as these things are flung out.
White dwarfs and remaining galactic material fall prey to black holes.
So gradually with time, what'll happen is the galaxy will have fewer and fewer objects in it, and a greater and greater fraction of them will be black holes.
And whatever isn't seized by the millions of black holes roaming the universe begins to decay with old age.
And this is another example of the general process by which the total amount of randomness increases in the universe. The second law of thermodynamics is once again at work.
And all the structures, all of these stars are basically evaporating into nothing. And so by about cosmological decade 40, most of the stuff that's been built, the planets and stars are all gone. And the degenerate era, which is stretched for huge amounts of time, is coming to an end.
With nothing left in their way, black holes stand poised to rule the universe. This may be the grim future of the cosmos. The planets decay and dissolve. Dark galactic remnants scatter across a bloated universe. And even light is just a faint, distant memory. As we continue through the vast stretches of time measured in cosmological decades, massive black holes survive as the only recognizable features of our once brilliant night sky.
We're up to about cosmological decade 60-something, and when you look out at the night sky, it's incredibly cold, it's incredibly black, and there's only the faintest crackle of radio waves and gravitational radiation echoing through the empty skies. This is the black hole era.
The continuous expansion of the universe has taken its toll. The unimaginable cold saps energy and constricts movement. Time itself seems to lose meaning.
In the midst of the black hole era, even the degenerate era looks like the first sliver of time after the Big Bang.
Does life have a chance in this environment?
Humans won't exist at that time because protons won't exist. But it's possible to imagine some kind of entity which is living at an extraordinarily slow rate.
If it lives slowly enough, perhaps strange life could emerge.
A thought would take trillions of years. It may take 1 trillion years for you to decide what to have for lunch because everything is so slow, everything is near absolute zero.
The creeping timescale of the black hole era can be compared to the growth of vegetation. From a human perspective involving minutes, hours, and days, plant life can seem frozen in time.
Absolutely nothing seems to be happening. It appears to be completely dead, completely static. But if we speed up the clock, then we see the activity. The plant grows, the plant moves its leaves in response to where the sun is. The plant is continuously in motion, it's continuously doing things. But that whole scale of existence is on a time frame that's longer than what our experience is used to dealing with.
The real action in the black hole era occurs when two black holes meet. Although invisible to human eyes, a collision between these two beasts sends a shudder through space-time. This event can be imagined in a sheet of perfectly still, calm water.
It's a bit like suddenly dropping a gigantic rock into that calm water, sending out a huge series of ripples. And you have a lot of action for a little bit of time, but then that dissipates, the ripples die away, and you're back to that smooth, glass-like sheet of water.
But even for these kings of the black hole era, time is running out.
And you might think, oh, they'll last forever. But even they don't last forever, because they evaporate very, very slowly with time.
Black holes in today's universe grow larger as they gobble up surrounding matter.
But eventually, far in the future, there will be so little material to swallow that the evaporation rate will start dominating over the rate at which they swallow material from their surroundings. So the evaporation rate proceeds more quickly when the universe is very, very old.
An evaporating black hole does not go out with a whimper, like the planets do when they die, but rather with a bang. That's because it behaves counterintuitively as it runs out of fuel.
There's basically two strategies that you can adopt. One is to sort of ease up on the gas pedal and try to conserve your energy and basically try to roll into the next gas station on fumes. The other strategy is to become impatient and floor the accelerator and try to drive to the gas station as fast as you can in hopes of getting to the gas station before your gas runs out. And the black holes are definitely taking the second route.
Unlike a car, when a black hole finally runs out of fuel, it explodes.
And in the last second of the black hole, when you're releasing megatons and megatons worth of TNT equivalent, a huge variety of particles that haven't been seen for many cosmological decades come spewing into existence and kind of flicker away in a last fireworks-like burst after the black hole is gone.
So after about a Google years or so, and the most supermassive black holes have evaporated away, what you've got left is a vast universe that is really almost entirely empty.
Next, the universe enters the dark era.
Now we're out beyond cosmological decade 100. We're in the middle of the dark era. The dark era, everything that we have now that is familiar to us is gone.
You know that expression, angels fear to tread? That's the dark era. The dark era you never want to go to because everything has crumbled. Not just the sands and monuments to man's folly, but even the atoms themselves have begun to crumble. Even black holes are not possible in the dark era.
If the universe continues to expand forever, it may be that only a cosmic mush of random particles remains. But a few surprises may yet rise out of these ashes. If, in the distant future, chaos does rule over order, our once glowing hot universe will descend into a chilling galactic ice age. But it may still harbor some potential, at least according to quantum theory, which examines physics at its most primal level.
In quantum physics, even the vacuum of space, that thing that we think of as being empty with nothing in it, is not actually empty. Quantum physics allows for everything to happen with some probability.
In other words, the universe is playing a risky game of chance, and quantum theory seeks to explain the behavior of particles in a universe where anything is possible. It's as if the universe were a card dealer continuously shuffling a deck, containing the very building blocks of our reality.
So if you have a bunch of particles in a quantum field theory, what happens is they're going to just rearrange themselves over and over and over again in what looks to us like a random set of fluctuations.
Quantum theory can't predict the result of a particle shuffle, but it can reveal the probability of each outcome.
If you have something that happens forever, an infinite number of times, even very, very unlikely things will eventually happen.
Ordinarily, when shuffling a deck of cards, the result is a random sequence. Likewise, particles churning on a quantum level don't usually create anything orderly. However, with enough time, any kind of quantum fluctuation can form, even one that seems impossible.
If you're in a universe that lasts forever, if you have a card dealer that is shuffling cards forever and ever, even unlikely events like that will occasionally happen.
One of these unique and improbable random fluctuations can change the fabric of space itself.
Empty space is kind of like water in the sense that it can appear in different phases. It could be hot and be vapor. It could be solid, like an ice cube, or it could be liquid. The space around us right now is in a certain physical state, but a phase transition can happen where that physical state changes into something else.
The wrong kind of random fluctuation can induce a devastating phase transition.
The way that would occur is that some region of space, some point, would witness the formation of a bubble, and that bubble would spread throughout the space around it, just like this ink would spread through the glass.
Just as the ink changes the nature of the water, so could a phase transition transform the nature of the cosmos.
The laws of physics would be different in the wake of this bubble passing. The masses of different particles would change. The charge of different particles would change. All of chemistry as we know it would be completely different after this phase transition occurred. And what that means is that suddenly there are new ways to arrange all of the particles that we're made of, and it's sort of like everything in the universe becomes an atomic bomb. It would just rearrange itself, releasing energy, and literally every particle, every atom, every structure in the universe would explode. So no complicated structure can possibly survive that sort of transition. What will be left is just a mess. Nothing but a gas of particles bumping randomly into each other.
But a random quantum fluctuation can also spark a bubble of hope.
Some theoretical physicists suggest that some of these quantum fluctuations actually can give rise to almost detached portions of space, dimensions that sort of branch off from ours into a new universe.
Perhaps a quantum fluctuation sparked the Big Bang and gave rise to our own universe.
So you can imagine that a universe like ours, even though it's 10 billion light years across, is actually a baby universe that arose by pinching off from some much bigger universe.
We can picture the birth of a baby universe with this bottle representing an old, dying, chaotic universe.
My breath is like quantum fluctuations, creating new universes that look like bubbles. And each one of those bubbles is a separate universe all of its own.
There is the possibility that there are other universes out there, perhaps budded off from our universe, and they may have their own fate, either eternal expansion or ultimate recollapse.
If other universes exist, then perhaps future civilizations may not face an irrevocable death sentence.
So I would suspect that trillions, quadrillions of years from now, when the universe gets really cold and the universe is near death, intelligent beings will be so powerful then that they may be tempted to assemble enough energy at one point to open up bubbles, little soap bubbles, gateways to another universe where it's a lot warmer, and they can start all over again.
Whether or not our descendants muster the technology to leave this universe, there's no avoiding the fact that, like all things, it will come to an end. While science wrestles with questions of how the universe will die, humanity is left to do the same with how it will live.
Our lives are important. I'm important, you're important, your loved ones are important, your friends are important, and we need to make the most of our existence during the fleeting time that we have here. This is your life, this is my life. We make the most of it, regardless of the fate of the universe.